Hello everyone, welcome back. So today we'll talk about flexures with the reinforced section. So we'll continue with the compliant mechanisms. And till now what we studied and what we covered is, so we have these flexures. So generally we call it wire flexures. So wire flexure, we understand that yes, under tension or compression, they have a very high stiffness. So it's along the longitudinal directions, so EA by L, but rest 5 degrees of freedom are there. So it constrain only one dot. So I think if we just go by the that principle, so this is one arrangement. I just printed out, so we can call it C1, C2, C3, C4, C5, C6. So here what we can see that total 6 constraints are there. So the center piece is completely constrained with respect to the frame. So yes, very slender element, and but it can be very effective. So yes, we really need to understand, and we have to feel ourselves. So if you have access to 3D printers, or if you can build some cardboard models, I think it's very nice. We also cover this, so sheet flexures, what we are calling many times. And yes, we use a pair and we can make cross flexures, so which will act as a hinge, or if it's in parallel, then it can we can design a parallel guiding systems. So in 2D case, what we realize that is just very slender element. So yes, under tension is very effective, and the stiffness we are talking about, it will be A by L. So the stiffness we get by virtue of the value of E, and yes, area of cross section we can increase and we can get higher stiffnesses. Yes, L, if we increase, the stiffness will be lower, but still compared to other stiffnesses, the bending stiffness, the torsional stiffness, the axial stiffness is way higher. So and that's how it works. So we can make different kind of arrangements and we can get a very nice design out of it. But we also understand that if they are going under compression, so very thin section, so is prone to buckling, and that's something we have to take care, or we may have to be aware of. So what to do? So yeah, I mean, intention, most of the things are fine, but moment it's a compressive load, we may have a problem, and we may have to ensure. So particularly with respect to the sheet flexures and wire flexures, we have to think about it. So these are equivalent. So we can always have an equivalent model. So as it deforms, then we can find the hinge here. Yeah, find the hinge, and okay, it's a supported. So we apply force F, and then okay, before it buckles, it's very safe. So what is proposed and what people have done is, what if we reinforce the middle section? So the span, the maximum span, if we reinforcing means we increase the cross section, so the rigidity will uh, be improved, and yes, the stiffness. So in this case, if we talk about this arrangement, what we realize that the stiffness is governed by these sections which are which are left on the either ends, and the middle section will have some uh, impact. So, we'll try to learn how it affects the performance. So, of course, we wanted to have a compliance, but at the same time, we also wanted to have the stiffness and the load bearing capacity. So, how things improve or degrade, I think we need to learn that. So, if we have that, and again we take a generalized case, so for reinforced flexures, so a section total length is there and P is, yeah, 0 to 1 if it's varying. Of course, yeah, it cannot be close to 1, otherwise, yes, it's the the entire thing will be rigid. 0, yes, of course, we can have 0. So, if it's 0, then yes, the entire section is slender and there is no reinforcement. If P is 1, then yes, the entire thing will be with the larger cross section, larger geometries. So, in between, if we have, so this is the compliant part, the stiffness of the middle section, the reinforced section is way higher. So, yeah, for the time being, for this kind of uh, analysis, we can always assume that that section is rigid. And if we do that, and if we apply a force F and moment M, we'll have deflection delta x and psi. And these are the material properties, and you have the geometry I, section values. So, area moment. And yes, in case of cantilever or any beam, we have already saw it and derived it. So, on similar lines, if we do, we can get the relationship between F, which includes the forces, force and moments, and then we have the displacements here, delta x and psi. So, and this is what we have, EI and this. So, this will be simply we can write as C times x, or we call it delta x. So, a stiffness matrix we have. So, coming back to reinforcement, when we do the reinforcement, what we also, as we learn, we realize that if we have this kind of flexures, so if we have the rigid model compared, then usually we have this um, hinges placed here and is somewhere around this 5 by 6 L. So, that is why we consider this case 5 by 6 L and 1 by 6 L on the either side, which is the compliant part, and then effectively what we get is length L between the hinge points. So, we will compare these two, and when we do that, what we realize, without reinforcement, if you start comparing and similar cross section, so the thickness, the area of cross section is the same. Only thing is we are playing with the middle section and we are reinforcing the mid section. So, in this case, it's a 5 by 6 L. If we reinforce, then what will happen? And so, if we have a similar kind of find the deformations, what we realize that these two values in both the cases is the same, because uh, sigma by y equal to m by I, if we compared in both cases, is the same for similar kind of configuration. So, the bending moment, it will not change. So, it will be same, the maximum value will be same, and that will be at the fixed ends. And if we just put the values, what we realize that the sigma max is not changing. It means the range of motion in both the cases is going to be the same, because if it's the same material, the sigma max will dictate what will be the total range of motion. So the jet displacement, if you are talking about, is not going to change this case, since sigma max is same. So we are not losing anything by reinforcing the midsection. What happens to Cy? So Cy, so in the y direction, this is the stiff direction, the longitudinal direction, and in the stiff direction, we want to have higher stiffnesses. So if it's not reinforced, it's ETB by L, so the area of cross section, and the length, total length in this case. What happens in the when it's a reinforce, it increases by this term 3, so 3 times. And if we look at it closely, what we realize that the effective length in this case, length effective is actually 1 by 6L and 1 by 6L, so 2 times L by 6, so which is L by 3. So effective length, the compliant part is only L by 3. So if you just use the formula EA by L, length has changed, it has reduced to 1/3, and therefore since it's in the denominator, the 3 will go up. So in fact, the Cy, it has increased 3 times, and it's a stiff direction, so it's a good. So with the reinforcement, we are getting better stiffness in the y direction, and which is 3 times, which is good. Now what happens to Cz? So the stiffness in the compliant direction. So Z is the compliant direction. If we move, it can move easily. So the stiffness should be lower because that's the compliant direction. So if you apply any actuation in that direction, it should deform easily. So yes, here EBTQ by L cube, we can always refer to the formulation. So if this is the case, then uh, for no reinforcement, that's the stiffness in the z direction. When it's reinforced, it increases by 20%, it's 1.2, so it's lowered. No, so yes, lowered in the sense that compliance is lowered. So if you are talking about in terms of a stiffness, we'll say okay, the stiffness has also increased, but this is something not desired, but okay, there is 20% increase, 20% increase, that is stiffness. So in the compliant direction, there is the 20% increase, and that's what we see here. In the stiff direction, it's 3 times, so it's much better. So let's look at the other parameters. What happens to the load bearing capacity? So Fy, so under compression, so if there is any compressive load here, Fk critical load for buckling. So it's end conditions are, yeah, they are moving in parallel. So for that condition, if you can assume, or for a cantilever, so it's a function of L square effective length 4 pi square Ai. So yes, this is the for no reinforcement, but moment we reinforce, the effective length here is L by 3, and if we take the square and in the denominator, we'll get 9 times. way higher, 9 times. So it's not 1 or 2 times, but 9 times. So if we reinforce the mid section by that amount, by 5 by 6L, and the compliant section is L by 3, so 1 by 6L on the either side, what we have observed that we are not losing any range of motion, so sigma max is same. Cy has increased 3 times, which is good. Yes, we are losing Cz, so compliance has reduced, so the stiffness has increased, so 20 times more. So here we are losing something, 20%. But in terms of the load bearing capacity, we are gaining a lot, 9 times. And that's why many times when we have these kind of designs, so if you are using sheet and wire flexures, and if we find that there might be some compressive load coming on these members, then it's always better to reinforce the middle sections, mid sections, so that the load bearing capacity can be improved. Of course, the stiffness is in the constraint direction getting better. Yes, we sacrifice a little bit of compliance in the compliant direction. So in this case, in the Z direction, it will be reduced. So the compliance will be reduced by 20%. So the stiffness will increase in this case. So we can see that by reinforcing, we are achieving a lot. And yes, we have to sacrifice a little bit, but on the other side, we are gaining a lot. So that's why it's a preferred. And again, we can also do the similar analysis if there is a, so what will happen to the normal stiffness Cy if, and if there is already a displacement here. And okay, for this case, when the guiding stiffness is high, is so in this case is infinite. So for this case, if we compare with respect to P, for different values of P, this is what we achieve with respect to delta x by h, and this is the stiffness in the y direction. And what we can see is for, yes, for almost 0.9, this is what we are getting. And so if it's not reinforced, this is what we have, P equal to 0, it may be lower, but as we increase the reinforcement, the stiffness will be better. So, and that's the reason we also want to have reinforcement, so that we can get a better stiffness in the bearing directions. Yes, we understand that the, in case of wire flexures, they are very good element, and they can provide one constraint, and we can use it as a building block to make different kind of compliant mechanisms with the different degrees of freedom. So that's how we can use that, but we also realize that it has certain limitations. So in buckling, yes, the load capacity will be limited in under compression. Secondly, getting a very thin section, thin members, and clamping it, clamping those members also very difficult. So the assembly will be challenging. So what are the other ways if you want to get the same behavior, the wire flexure, but can we work around? So very good example here. So manufacturing wise also is easy to make, but assembly wise also I think it's a very good. So if we just fix it and then apply the loading, what happens in this case, we can start with the very flat member here. So flat is stiff with the cut here, and then there is a fold line defined. So if we just fold it from there, and this is what we get. So if we fix it and then try to move, so we can see ourselves if we try to move in different directions. And then even the rotation, if we try, but we realize that is a constraint in the x direction here, along the length, along the fold line. So what happens if we just try to see one by one along x? Yes, everything has to be stretched. And of course, in this case, EA by L, and this section actually will determine what will be the stiffness in that direction, because area of cross section is almost half in that case. Length is also small in that case, but we may need to compare, like which one will determine the overall stiffness in the axial direction. But still, it will be higher than whatever stiffness we have in the other direction. If you try to move in y direction, if you try to give this force, this is a stiff, this is also stiff, but this can easily bend. This can bend easily. So it's a compliant member. If the force is in y direction, what happens if we have the z in the z direction? What we realize, this is a stiff, this is a stiff, but then this can flex, or other way around, we can say it can flex this way. So we it's a we can see there is a compliance in the z direction as well. Likewise, if we talk about the rotation, yes, it's torsionally compliant member. All the three are torsionally compliant member in X, so it can twist easily. If it's in Y direction, so this can twist easily. If it's in Z direction, this can twist easily. So what we realize that except X, all are compliant. So it can easily replace any wire flexure. So yes, we can start with the simple configuration with the constraint line approach, and we can assume it's articulated line, or later we can um, also assume that is a wire flexures, but we can always replace that wire flexure with this kind of embodiment. So it can be a reinforced flexures, or it can be a folded sheet like this. So single piece of steel folded in this way can substitute a wire flexure, and we can also check the what will be the limiting conditions if there is a compressive load. So it will be much better than wire flexure, and it's easy to manufacture also, because we can take any sheet metal and just stamp it and fold it, and then we can easily either weld it or either clamp it. So we have area to work with, and uh, it's definitely easier fabrication wise and assembly wise. For reinforcement, not necessarily we have to remove the material all the time, but one can be very clever, and for instance, in this case, you have the wire, but then you just use the thin tube and just insert it, and you can see the gluing here. So similar features we can get. What we also realize that this also allows or give us more area for clamping and for assembly. So this is way better than just securing a thin piece of wire. And of course, this is the middle section, which is compliant section. So this way also we can get a reinforcement. We can reinforce the mid section, and we can always get a better performance. So there are some simpler ways to achieve the kind of wire flexure. So this is like a steel wire and flattened it both ends. So it acts as a U joint, inverser joints at either ends, and we can get it from the uh, poly- polypropylene injection molded product also. So we can make hinges here in orthogonal direction, and we can get a similar performance. So what we also realize that simple flexible wire can also provide us the required constraint in one direction. So if it's intention, and if we can ensure that the kind of loading in the wire is always in tension, it can also give us very good constraint device or constraint mechanisms or compliant mechanism, what we can say. And unknowingly or knowingly, we have various examples. So in any kind of belt drive or cable drive, what we see these days is routed, and if we are able to ensure the proper tension in the in those things, it can it can move very easily, but it can be it can provide a rotational constraint. So many parallel guideways, they are secured using cables. So this is what is there. Yes, clamping is issue, so many times we have to check how to route it and then clamp it, and pre-stress rod to get that tension in the cables. And like in many designs, we can have a springs here pre-tension, so that the loading here always in tension. And here again, very beautiful mechanism, parallelogram mechanism. So two parallelograms, and what we find that is rotationally stiff. And earlier we used for drawing and any kind of architectural drawing or machine drawings, we use these kind of mini drafters. So very good mechanisms, and it can be still used in many applications. So similarly, we'll have other kind of flexures which is very popular. So what we generally call it folded sheet flexures. So we take one sheet and then there is a sharp bend. So this is very important. The bend has to be sharp, then only we'll get uh, this property. It constrains only one dots. So again, it's equivalent to wire flexures along this line. So along the fold line, so if we have a configuration with the wire flexure, we can always replace that wire flexure with the folded sheet flexures in this way. So the constraint direction is the z direction, which is along the fold line. So this is the sheet flexure we are talking about. And if we fold it 90-degree bend, not necessarily 90-degree, but yes, it should not be close to 0 degree or not towards also 180-degree. But if there is a fold line in between, we will get a very good constraint device in one direction, and that is one constraint along the fold line, and many times we call it FSF, folded sheet flexures. Again, because it can be easily made, and the assembly wise, fabrication wise is very good. So uh, that's why it's a preferred choice, and the range of motion is also very large in this case. So just to understand, if we have this folded sheet flexures folded in that way, and if H and T is same, yes, the lengths are different, A and B, the two sections A and B different. So it's a grounded here, so fixed, but this is the moving part. And if we apply force Fz along the fold line, so that is the z direction, so the associated deformation is uz. What we realize that is the constraint direction, and the stiffness in that direction Fz by uz is given by the bending stiffness, and again is the stiff direction, so bending stiffness as well as the shear, both are working, and is so the deformations will be added, so compliance will get added, and that's why you have these two parameters. And it's inverse, so we are adding compliance, so that's why it's the inverse. 1 by Cz will be equal to these values. So, and that's why we have the inverse minus 1 power. So, be aware of that. So, I just want to remind that yes, we don't want anybody to remember this big equation. So, wherever required for examination purposes or for any kind of work, we can always refer to the notes and we can work with that. Or yes, for the examination point of view, yeah, definitely if it's required, then I can always provide you with the general equations. What one needs to understand that how to use it, what are the boundary conditions, what are the parameters there, can you how to replace that and get those values and use it. So that's more important. So we'll practice and we'll see how to find these numbers. So if this is the case, if we use folded sheet flexures, what we also realize that, just take one example. So we are talking about fold lines here. So these are like three leg supported on. So it's like three-legged table. This is how it will look like. Only good thing is, in this case, it's a floating. So the green part floats around, and this C1, C2 and C3 is supported on those three legs. It's very similar to this. Of course, if we have the flexure members here and try to use, it will flex, and similar to parallel guidance system, what we also realize here, there will be shortening effect if there is any deformation. One good thing about using folded sheet flexure, we don't have that shortening effect because it's still floating. So the plane will be remain there. So and so we can achieve a planar motion, and what we see that we can get x, y and theta motion. And if we do that in that way, and it will be constrained in z direction, and the out of plane rotation, that is theta x and theta y, it will be constrained. So we'll get three dot system, planar dot system, very nice, and very good use of folded sheet flexures for making these kind of things. So just a general case, if we apply force Fx, this is how it deforms, A and B different length. So if we take this case, so we have forces Fx, Fy and M acting at the end. So all the compliant direction we are talking about now, and that these are the associated deflections. Again, this is within the elastic range, and we are talking about the mm, elastic range of motion. So it will always come back. It works as a spring, though it will be non-linear, but if there is a force, there will be deflection. If we remove it, it will come back to its original position. So if we have this, we can always write the deformation with respect to forces and also write in a matrix form. So 1 by EI, and then this entire matrix can be written as A, different values A and B. So we can also write in terms of stiffnesses matrix. So F equal to Cu, so A inverse will come here, and this is, so this will be the stiffness matrix in this case. So X, Y and phi. And what if these lengths are same? So from here itself, what we can see, if we just take this member 3 times, this is 5L divided by this 2 and L to the power 3 and 4. So 15 by 2 L cube. So similarly, we can work with other elements, and what we find that if A is equal to B, and generally we can say simply L, same length, then this will be the stiffness matrix. So I just showed 15 by 12 Q, and similarly we can derive all the terms one by one. So this is the stiffness matrix for this generalized one. So the end is not fixed. There is no boundary conditions applied here. This is the case. But what happens whenever we use these things in a system, they will be assembled, and because of the geometry, because of the overall constructions, certain boundary conditions will be applied, and then we can easily find the stiffnesses in different directions for that system. So for instance, if we have this kind of things, it's supported like this, what will happen? What will be the stiffness? So we can find that what will be the stiffness in the x direction, right? One need to understand, what are the boundary conditions imposed here? So I think one should be very clear about that. It's not m equal to 0. M will be always there. What is there is, if you are calling it psi, the angular deformation, this is 0. This is not changing. It's a fix, and that's why we have the roller. So we can have x, this is ux, and as it moves, it's a guided. So m is not 0, it's the psi. Psi is 0. The angular deformation, so it's a guided. But there will m is not 0. So we have to remember that. Similarly, y displacement is also 0. Is still going along the guide. So y is 0 in this case, not fy. Fy is not 0. So I think many times this kind of mistakes students they make in the class whenever we ask what are the boundary conditions. So I think one should be aware of, and the rest. So if we are applying fx, these are kind of reaction forces. So Fy and M, and that's why these are the forces we are talking about. One is the actuation force, other will be the reaction force. So Fy and M. The displacement is Ux, and when we do, this is the effective stiffness in the x direction. Again, we can also calculate the stresses, and what we realize that the at F and clamp there will be, because the way it's deforming, the way the boundary conditions are placed, we have different stresses. So we have to find the maximum value, and these things we can easily also use any CAD packages and also do the analysis. What happens if it's like this? So in this case, x is 0, and again this is also 0, and only displacement we have is uy, and again we have one actuation which will be like fy in this case, and fx and m will be the reaction moments and forces. And again we can also find the in along the y direction what will be the stiffness, so fy by uy. So this thing will come into the picture, and likewise we can have the bending stresses, and the maximum value will determine what will be the range of motion. Similarly, we can also have this kind of arrangements, and we can again find the stiffness matrices and the bending stresses. Likewise, we can get this kind of formulation. So it's again one DOF only. We are giving actuation, and this is kind of constraining equation. It's only coming along the slope. So here we may have ux and uy, but they are not independent. They are only one parameter can be independent, other is following it. Again here phi is again phi or psi, whatever angular deformation we are calling it. it will be again 0 because it's following a plane. So the stresses we can have, and we can also calculate again the range of motion. So we can summarize and we can get these things, and yeah, in the references we can get all these. So depending on how we are using it in the system, we should be able to refer it and use the equations accordingly. So we'll take some cases and also try to find the some values. So for instance, the stiffnesses in different directions, and we'll try to use these formulations and also otherwise also. So some of the concept of like what is the effective stiffness, the transmission ratios, all those things we can use, and we can also calculate the overall stiffness. For instance, if you are using that planar thing using 3 folded sheet flexures, what will be the overall stiffnesses in the different directions? What will be the stiffness in the bearing direction or the constraint direction? So we should be able to calculate. So we'll take some more examples and try to explain. At the same time, there are a few more types of, I would say, flexure elements, which are like a use and build system or mechanisms with that. So we'll talk about that in the coming lectures. Thank you.